So what's this 1 plus x? So we're on the same page. So I want you to find the third degree Taylor polynomial for log x with center x equals 1. So do you remember log x? What the expansion is with x equals 1? Does this look familiar? That's the first example we did today. X minus 1 minus another 1/2 x minus 1 squared plus minus so the idea is log x is these infinitely many terms put together. And then if I want to get an approximation, and so I'll just take finitely many terms. And what you want to be careful of is the number here represents the exponent we stop at. So if I'm asking for t3, I start taking all the terms until I get up to an exponent of 3. So I'm going to kind of blend together 1110, the last part of 1110 and 1111. So I think technically, I think what I'm doing now is an 1111. I'm going to come back and do the tail end of 1110 in this context. Actually not. So let's find T1, T2, and T3 for cosine x. I don't know if you have this memorized yet, but you might want to do it sometime between now and 3 weeks from now. So cosine x is this. This is where you want to be a little bit careful. Circle this one. Is which one is this? 1 minus 1 over 2 factorial x squared. That's T2. A couple of things. Let me write this out the long way. So that's what it's going to look like if all the zeros are there. T1 of x 1 plus 0x, which is just 1. T2 of x is this part, 1 minus 1 over 2 factorial x squared. And then T3 of x is the same thing. So the first degree approximation is the 1 plus 0x, which just simplifies to 1. The second degree is we go out to x squared. And the third degree, we go out to x cubed. What's kind of interesting about the cosine is the x cubed part has a 0 coefficient. So I'm going to throw this out there now, and we'll come back to it later. We're going to do an error analysis. We're going to talk about how bad the error could be if we use one of these approximations for the function. And the error is, among other things, is going to depend on the n value that we pick. So the error formula is going to have an n in it. The larger the value of n, the smaller the error is going to be. So you can do an error analysis for n equals 2. You could do that same error analysis for n equals 3. And since t2 equals t3, you'll have a better number with n equals 3 than n equals 2. So just keep that in the back of your mind, and I'll explain it more as we get there. And let me show you something interesting about cosine. So here's the linear approximation, which you see isn't a very good approximation to cosine. What shape is T2? So if there's an x squared, what shape does the graph have? It's a parabola. Is it happy or sad? It's sad. So the T2 graph is going to look more like this. And you see how T2 is a pretty good fit for cosine around there? So T1 is terrible for cosine, T2 is a good fit. And what about the sine graph? Remember, the sine graph looks like this. And T1 of x. So it's actually, at least if I'm close to 0, T1 is a pretty good approximation for sine. Terrible for cosine, good for sine. Then, let's do one more term. So I've got my e to the x, and I'm going to, as my approximation, I'm going to peel off everything up to x squared. It's the part I'm left with is the R2 of x is how close the approximation is to the actual value. And we used the Rn before. The only difference is now it's a function of x. And then our job in the very near future is to see what we can say about the error. So this R2 is our formula for the error. So it's the error we get when we're approximating e to the x using the T2 approximation.